Hi everybody. So here's a problem that was asked to do, which was Chapter 6, Problem 65. So let's do it. All right. So we got a 22 kilogram child, that's the mass, is riding on a playground, riding a playground merry-go-round that is rotating at 40 revolutions per minute. That's an awkward frequency. What centripetal force, again, don't really care for that term, basically they're saying F net. This is just F net that they're looking for. What's the net force? Is exerted if he is 1.25 meters from its center. So that's essentially my radius. And let's just focus on that right now. So let's do part 8 here. So I already drew my diagram with a circle. I know it's got a radius r that I know is 1.25 meters. They gave me a frequency, which is 40 revolutions per minute, which again is a kind of an awkward frequency. And then I know the mass is 22 kilograms. All right. So, and basically I'm trying to find the net force. So basically I could say, all right, let's say the child is here, right? There's going to be a net force pointing in the towards the center of a circle because the child is moving at a consistent frequency. That basically means that they're also going to be moving at a constant speed. So I'm now going to apply F net equals ma. In this case, the net force, which is the quote-unquote centripetal force. Again, centripetal force is just F net when moving in a circle. So, and that's what I'm solving for, F net. So is going to be the mass if I'm moving in a circle. In uniform circular motion, I'm not speeding up or slowing down. It's going to be v squared over r. Or another way that you could write that, I'll write that over here. So recall that tangential speed is equal to the angular speed or the angular frequency multiplied by the radius. So if I have v squared over r and I replace v squared with omega times r, this becomes distributing the square. I get omega squared r squared over r, and then r cancels here. And another way I could write the centripetal acceleration is omega squared, the angular velocity or the angular frequency multiplied by the radius. So, and that's what I'm going to do this time. I could totally just plug this in there and then convert this to an angular frequency, but I'm going to get fancy. I'm going to get fancy, and I'm going to say this is my acceleration, omega squared times r, and that's what I'm going to replace in there. So instead of so basically I'm going to use another way to write the centripetal acceleration as omega squared times r, and I just showed it to you over there. So I'm going to take that, plug that in for there, and this is going to be omega squared times the radius. So I know the mass, this is the mass of the child, it's 22 kilograms, so I'm good there. I know the radius, it's 1.25 meters, but now I need to figure out what omega is in order to solve for this thing. So I'll plug in everything right now and then get omega squared in just a moment. So 1.25 is the radius, and let's go figure out omega squared. Or just omega. So basically what I'm going to have to do here is I know that I have a 40 revolutions per minute frequency. So I want to convert that to seconds, because here's the thing. Omega, angular frequency, is specifically defined as being radians per second. That's the point of it. So I was thinking of using your equation sheet. You could use your equation sheet. On your equation sheet, they basically say, I think they say like 1 over the frequency is equal to 2 pi over omega. That's one of the ways that they show it. I think they also say the period is equal to that. They do something like that. But I'm going to do it just using conversion factors. So I want to get minutes to seconds. So I know 1 minute is equal to 60 seconds. And then lastly, I know 1 revolution is equal to 2 pi radians. And that's going to get me my radians per second. Minutes cancel out, revolutions cancel out, and I get radians per second. So I'm going to multiply across here. That's going to be essentially 80 pi over, so multiplying those, divided by 60's left over in the denominator. So I'm going to write this into my calculator. I got 80 pi divided by 60. I get about 4.2. So I'm getting about, so that would be my omega then is 4.2 radians per second. And then I could plug that in for my omega here. So that's going to be 4.2. And then let's get this over here. So my net force, and plugging in all that, that's going to be 1.25 times 4.2 times 22 is about, I'm getting about 115 newtons. And there we go. That is my net force, or my centripetal force, or in other words, that's the net force that's causing the centripetal acceleration. All right. Now for the next part, what centripetal force is exerted if the merry-go-round rotates at 3 revolutions per minute and he's 8 meters from the center? So basically everything here is going to be the same. So I'm just going to carry this over for part B. Everything is going to be exactly the same. So this is still 22. Let's see, 8 meters for this, and now I got to get my omega squared. My omega squared, and this time I'm going to do the same thing. The conversions are even all the same, so I'm just going to copy all this over. Except now, instead of 40, I have, they told me it's 3 revolutions per minute, and that's basically it. So this is 3 revolutions per minute. So this is 3 revolutions per minute. There we go. There we go. 3 revolutions per minute. So everything's all the same, except now I got 3 times 2 pi, which is 6 pi over 60. So plugging that into my calculator. Uh, 0.314, I'll say. So 0.314. And now that's in radians per second. And I could take that, plug that in there. So this is 0.314 squared. Oh, just realized I think I made a mistake in that previous one. Let me correct that in just a moment. So I got 0.314 squared times 22 times 8. So that's going to be about 17.4. So my F net here is 17.4 newtons. There's that. I think I forgot to square this. So if I square this, yeah, let's see if that changes things. So it's going to be 4.2 squared times 1.25 times 22. Now I'm getting 485. So that changes things. Sorry about that. So if you caught me, hopefully you yelled at me. And there you go. There's the change. I hope that's correct. At least the process is correct. So it's 485 now. And then this one would be about 17.4, which makes sense. We're going slower. So if you go slower, you're going to need less force in order to keep it moving in a circle. At that, and our radius is bigger, right? So we're going slower, and our radius is bigger, and so that's going to cause for, yeah. All right. So on to C. It says compare each force with his weight. So his weight is just going to be mg. And so I saw some students kind of just comparing the force with the weight, which is fine. I'm going to take the ratio and see how many times the weight that is. So for, let's see, for part A, taking the ratio of the force to his weight. So the force we got was 485 divided by his weight, which is mg. So it's going to be 485 divided by essentially 220. That's 22 times 10. So essentially we get a little over, it seems like a little over 2. So 485 divided by 220, yeah, 2.2. So about 2.2 times his weight. Where if we do this for part B, same idea. This time though we get 17.4 divided by mg, so 17.4 divided by 220, and we can definitely see that it's less than his weight. How much less? Wow, quite less. So 0.079. So that's a little over 12 times less than his weight. But we could say times his weight here. So kind of getting that ratio kind of gives you an idea of how big that force is or how much that force is. But yeah, people who did it qualitatively too, that's fine because it didn't ask you for anything in particular. All right, so I hope I made that correction clearly and hope that helped. All right, bye.